Hello friends, I am back with a new problem today. Let's see this problem. The problem statement is there is a heavy rod whose density varies as rho equal to a plus bx, right? And its Young modulus is y. Its length is L. This rod is hanging at x equal to 0. So find the elongation of the rod due to its own weight. So let's try to understand the problem first. This rod density is varying according to this formula rho equal to a plus bx, right? So it's not uniform. At x equal to 0 its density will be a, and at x equal to L its density will be a plus bl, right? When we see density, uh, it's basically mass divided by volume, right? Now uh, its Young modulus is given as y. So what is happening is because of its own weight there will be some stretch in its different parts of this rod, and then because of this stretch there will be total elongation in this rod. Okay, so that's the problem. Let's solve this. Okay, so solution we are going to discuss now. So what will, since this is not a uniform rod, you cannot just apply Young's modulus formula y equal to stress by strain, right? Because how will you find the strain? How will you find the stress? So let's consider a small portion of this rod, okay, at a distance x from the point where it is attached, right? And then a small portion is of length dx, okay. And let's assume that its cross-sectional area of the rod is A. Let's assume that that is given in the problem. Cross-section of the rod is A. Okay. So what will be the mass of this small portion? This dm will be volume into density. Density is rho, volume will be dx, and then cross sectional area A. So this is your volume. Okay. Now let's consider this part. So what is going to be the weight attached to this part, this lower portion, right? If it is x, this lower portion will be L minus x, right? You can, this ds is very small. Actually this will be L minus x minus dx, but since this is very x, ds is very small, you can neglect this dx. So effectively it will become L minus x. Okay. Now you can treat the system like this. There is a, let me draw the free body diagram of this. So there is a, this portion of the rod, and then let's say this is attached to a small string like this. There are three portions, right? This is x, this is dx, and this is L minus x. So because of this L minus x, there will be some force on this one towards downward, which is pulling this smaller portion downward, and then this portion is pulling this whole one is downward. but we are not going to consider this portion right now. We are just interested into this smaller part dx. So what is going to be the weight of this? This is the weight which is stretching this smaller portion, right? So let's consider this is a b c. So weight of c will be mass times gravitational acceleration. What will be its mass? So L minus x. L minus x is its length. Its cross sectional area is A, right? And its density is rho. So this is your mass multiplied by G. This is the weight. So this is the weight of C, which is pulling the body B, right? Now we know Young's modulus Y equal to, let us delta L, the change in length by original length. Sorry, I am telling opposite. It is force, right, per unit area. So force per unit area F by A divided by change in length by original length. This is your Young's modulus. So from this you can find out delta L by L equal to F by AY, or delta L change in length equal to FL by AY. This is the formula I have just written, right? Now let's use this formula in our case. So in our case, I have just considered this smaller part, right? This is smaller part, original length was dx. So what we are going to find out is the elongation in this smaller part, delta x of this dx, or delta L of this dx, right? What is going to be the elongation of this smaller part because of this weight? So elongation in smaller, smallest, I can say, right? This is very small, smallest part B will be F. F is how much? F will be mg, which is weight. Mg we already found out, L minus x, right, into A rho g. This is mg divided by cross sectional area is A, and then L is dx, this small element original length, and then Young modulus Y, right? You can cut this A and A. Okay, so what it become is L minus x, rho we will put the value now. Rho is how much? A plus bx. L minus x, A plus bx into g dx. A we already cut it, right? So A gone, only y is remaining. So this is the elongation of this smaller portion in this smaller portion. So if you want to find out the whole elongation in this whole rod, you just have to integrate it. That's it, right? This is a technique we use for anything which is varying. So we're going to integrate it from 0 to L, and then we'll find out the total elongation. So total elongation in the rod will be, integrate from 0 to L, and then this is the one, L minus x into A plus bx into g divided by y and dx. Now this is just a plain mathematics. You can solve it. What it will become? It will become, just let's solve it, LA plus BLX minus AX minus BX square, right, into G by Y dx, 0 to L. G by y we will take out common. So LA, integration of LA will become LAX, right? Plus BL, x will become x square by 2 minus A, x again will become x square by 2 minus B, x square integration of x square is x cube by 3, and put the limits. If you put these values, what it will become? Let's put the upper limit first. L A and then L plus B L into L square by 2 minus A L square by 2. Okay, minus B L cube by 3, and then once you put 0, all this term will become 0, so you don't have to put right. So if you just solve it, G by y, A L square plus B L cube by 2 minus A L square by 2 minus B L cube by 3, G by y, let's take the LCM of 2 and 3, it will become 6. A L square will become 6 A L square plus 3B L cube minus 3 A L square minus 2B L cube is equal to G by 6y. 6 L square minus 3 A L square will become 3 A L square. 3 BL cube minus 2 BL cube will become BL cube. That's it. Elongation. So this is the elongation in the whole rod. This is what we needed to find out, right? Let's do a recap. So since the density is varying, right, and then since we need to find out the elongation because of its own weight. If you see, weight is varying, right? Weight on here will be more because of this lower part is more. Weight here will be half of the rod weight, right? And then weight here will be very less because only this part will be there, which will be stretching this portion. So since weight on a specific point is varying, we cannot solve it by directly putting y equal to stress by strain formula. It's going to be a variable case. That's why we took a smaller element dx, and then we just solved the problem for the dx, and then we applied the magic of integration from 0 to L. Right? That's it. Here we found dm, but this is not needed. We just found it. It is not being this part. This part is not utilized. Right? So we just found out the c weight. C is mass times gravity, and mass is L minus x, length into cross section area A, right? And then mass volume into density rho g, and then we know the formula y equal to stress by strain. So from this we found out the elongation is this, and now this is the elongation. If you try to take this smaller element del dx, what we did, we just put these values whatever we found earlier. So this is we found the elongation in this small rod dx, small portion of this rod dx. And now that we found the elongation in this small portion, we integrated this from 0 to L, and that way we got this answer. Okay, I hope you enjoyed this video and learned from this video. If you like this, if you learned from this video, subscribe and like this video. Okay, we'll meet in the next class with some new problem. Till then, bye bye.